Good morning. Happy Monday. Shall we call this coffee and cleaners? I kind of like that. I thought I'd share with you this little booklet from the Spencer Turbine Cleaner Company that is over 100 years old at this point, and it is full of fascinating information. I don't know if this was given out when you purchased a cleaner, if this was sort of shipped in the box as kind of an installer's guide, or if this was a promotional thing. But we'll go through it. I'm going to move the coffee a little bit. So this describes what a built-in vacuum system is in general. At most 25, 50, or at most 75 foot length of light flexible hose, strong, slim, and light cleaning tools and handles. Successful vacuum cleaning is essentially pumping dirt, not clean air. Mere air handling efficiency, therefore, should be secondary to practical dirt handling, from which it follows that only simple, sturdy, wide-clearance vacuum producers that will permit the use of simple, sturdy separators should be used. That's a good little tongue twister there, Ira. Hose is the largest factor of maintenance, causes greater vacuum loss than any other part of the system, requires labor and handling, and eventually wears out. Plenty of piping and short hose runs are necessary, and the most economical, besides rendering the entire equipment much more rapid, efficient, and easily handled by the operator. There is still some debate about that today, whether it's better to deal with big long lengths of hose or whether it's better to change inlets all the time. Smooth uniform bore throughout the pipe and fittings, long-term drainage or Durham fittings. Horizontally disposed cleanout plugs at the foot of risers have proved satisfactory. Long sweep pipe bends should be used at any points where the dirt is required to go from a horizontal pipe up a vertical one. So actually, instead of a fitting, take the pipe and bend it, give it a real long radius sweep. And in fact, today, if you look at the industrial vacuum fittings, the big bent steel ones, you can get them there. It is a pipe bend. It's just been made into a fitting, and anything can go through there, and you wouldn't get stuff stuck at the bottom of a riser. Piping should not be so small as to require too high vacuum, high velocity, nor on the other hand so large as to reduce the velocity sufficiently to prevent dirt settling. So there is a sweet spot for piping. Service or intake valves. I like how they call the inlet valves intake valves at this point. It sounds more forceful than just inlet. Going through specifying the hose material. Heavy duty, where sweeping is mostly done by men, such as good-sized banks, churches, clubs, factories, post offices, hospitals, hotels, libraries, office buildings, blah, blah, blah. 1.5 inch oil-tempered ribbon steel reinforced rubber or heavy duct covered, highly flexible, weight 8 to 10 ounces per foot. Medium or light duty, 1 to 1.5 inch oil-tempered ribbon steel reinforced. Exceedingly flexible, weight 4 to 6 ounces per foot. I wonder what our vacuum hoses weigh today. Probably even less than that for 1.5 inches. The modern Spencer literature does show the weight of different hose materials. Stems should be not more than 1.25 inch diameter and of steel tubing, weight from 3 to 6 pounds according to class of installation. Plain slip joints or taper connections are unsatisfactory. At this point, the Spencer swivel handle and the Spencer locking coupling had already been invented, the stuff that they still sell today. This is neat. The average vacuum cleaner salesman will sell just as large a vacuum cleaner equipment as the customer will purchase, regardless of the true requirements. The following rules afford a reasonably accurate and definite method of determining the sweeper capacity of plant required for any given building. Heavy-duty standards for 15-inch tools. They want a minimum of 2 inches of mercury with a 7/8 inch orifice in the Spencer vacometer for bare floor cleaning, and 3 inches of mercury with a 5/8 inch orifice flowing for carpet cleaning. And of course, mercury translated to water lift, that would be about 30 inches and about 45 inches respectively. So 13.59 times the mercury reading to get inches of water. And of course, if you use smaller tools, then you don't need quite as much vacuum to give the same velocity. This paper is so thin, I should probably be wearing gloves for this. Medium and light duty standards. So if you're really not as concerned about cleaning as rapidly as you possibly can, Spencer's word was rapid and thorough cleaning. If that's not as big a priority, then you can downsize the machine and you don't need quite as much. But these formulas here, so this number below the line on each one of these is the amount of square footage per hour each operator can cover, depending on whether it's heavy duty or light duty. So 7,500 square feet per hour if you have the heavy duty formula and you have at least 2 or 3 inches of mercury at the end of the hose, or it goes down as low as 2,500 square feet per hour if you are only getting either 1 or 1.5 inches of mercury at the orifice size at the hose end. And they've actually worked this out, that, you know, they did studies, figure out how long it takes a guy to vacuum this this area, and that's your formula. This is a cross-section of the drainage fittings showing the recessed hubs. So even though these fittings look like gas fittings or water fittings, they on the inside are different so that you get a smooth flow from in and out of each fitting. Long-term recess fittings should be used wherever space permits, but short-term may be used in narrow partitions on vertical pipe only. Now today you're really supposed to put a short radius fitting behind each valve, whether you can get a long one in or not. So that has changed a little bit. This is cool. These are cutaways of the inlet valves installed in the baseboard. You can see the lath and the plaster keyed into it and the baseboard cut out for the valve. This will be the flush mount valve. And this will be the more common valve that sticks out a little bit, but the hole is not as big through the baseboard. And actually the diameter of the whole valve trim escutcheon is not as large. Found more desirable because of its smaller outside diameter, presenting a neater appearance. Only requires a 2 1/4 inch hole in the baseboard. And here's your close clearance intake valve. It's got a 2-inch pipe fitting to go right into a hub of a 2-inch fitting. And here's a surface mount valve for exposed piping. So here's our machine specs. The designs of these machines make this from probably 1915, 16-ish. This is your 1/2 horsepower. This is the little guy that you'd see in houses that theoretically they would sell the most of, but I have yet to actually acquire one. I've had a few kind of slip through my fingers, which are hopefully in happy homes. This would be a universal motor up here, not an induction type. And this is where they started using induction motors, and this is a 4-stage turbine. The one on the previous page is a 2-stage. This machine design with the big removable clean-out door instead of the smaller hinge door means it's after 1914, because my 1914 machine has the smaller hinged kind of door. And here's the 6-stage 1.5 horse machine. So I've got one of these. The motor looks different. Well, my motor's been replaced, sadly. But yeah, they've gone up to a 2.5-inch intake and exhaust on this, even though it's still for a single operator. Just because this would have been in that much larger of a home with that much longer piping. So they wanted you to upsize to 2.5 for friction loss. Oh, and here's a cool one. Boy, if I ever come across one of these. 3-horse vertical with the separate cyclonic separator. And this will be a 1, 2, 3, 4, 5, 6, 7, 8-stage turbine driven by a 3-horse motor. These are where you really get into the ones that could suck the paint off the wall. And then here's a 5-horse vertical. This will be before they went to horizontal turbines for the smaller sizes like 3 and 5 horse. This will give you a 3-inch intake. So this is getting into, the 3-horse will be for 2 operators. This is getting into 3 or more operators on it. 28 inches diameter, 66 inches tall. Boy, imagine what one of these things weighs, all that iron. That's the thing, if I do ever come across one of these, what the heck am I going to do with it? And at this point, all of your larger sizes were made in the classic Spencer. They call this the sugar scoop design here. 10 through 25 horsepower. 4 through 6-inch separator intake. All the turbines had a 6-inch exhaust similarly. So like at the Fox theaters, they used a 20 or 25 horse unit. And that was to enable 6 to 8 people to vacuum simultaneously because they wanted to be able to turn over that entire theater very quickly between shows. And this was before you could get a Spencer one-piece cast hose hanger of the type that I've shown in other videos. So they gave you these 3 brackets and they showed you how to put them on the wall in a given radius to hang the hose. And here's that Spencer hose coupling. Patented that over 100 years ago, still sold today. Now this gets pretty technical. This one is pitot tube measurements, which is the little tube that goes into a pipe and then turns to go like an arrow pointing toward the airflow. And so the air rushing past it induces a vacuum in that pitot tube, and you can measure the air from that. And this shows you loss in inches of mercury vacuum in 100 feet of hose. And they misspelled vacuum. I'll have to see if Spencer can send me a new one with corrections. Yeah, right. Different hose diameters and different airflows give you different vacuum losses. So if you want to know, okay, a 1.5-inch hose flowing 80 CFM, you're going to lose 4 inches of vacuum. So this relates back to the heavy duty and light duty standards that Spencer talked about in the beginning of this book. So if you need 3 inches of vacuum at the end of the hose and you're losing 4 inches of vacuum through the hose, then you need the producer to maintain 7 inches of vacuum plus whatever your loss is through the piping. And this will get into that too. And this is, what is this? Inches of mercury, vacuum on the gauge. This is just a conversion chart. Velocity of air in feet per minute for various pipe sizes. So you can see again, if you're flowing 80 CFM, which is about what you flow for one operator, through 2-inch pipe, it's flowing at 3,666 feet per minute. But if you go up to 2.5, it's flowing at over 1,000 FPM less than that, which will reduce your friction loss. Vacuum loss in inches of mercury. So then, arbitrary, take the 80 CFM again. For 100 feet of pipe, you're losing 0.62 inches of mercury. But if you only ran 1.5-inch pipe, you're losing almost 3 inches of mercury. What a difference. That's amazing. And then, let's see, on a big, gigantic system, if you're flowing 400 CFM through 4-inch pipe, you're losing a half an inch of mercury. In 5-inch pipe, you're only losing 0.15 inch. So they really had a scientific approach to vacuum cleaning in these days. flow meter volume through. Okay, so this is interesting. Remember back that the heavy duty standards, they wanted 3 inches of mercury at a 5/8 inch orifice, which gives you 38.7 CFM. They wanted 2 inches of mercury at a 7/8 orifice, which gives you 56.2 CFM. That was the least that they said would give you rapid and thorough performance. It's not actually that much, interestingly enough. And this is interesting. This is the same data but measured by a different measurement. So they're kind of proving to you that they've double checked their math. And this is 5/8, 3 inches gives you 50. 7/8, 2 inches gives you 92. Interesting. This is quite a bit higher on this page. Effect of altitude on volume and density of air. So you guys installing central vacs in the mountains, you know that you get a lot more airflow but a lot less water lift up there. And oh, this is neat. Okay, so this is a recording vacuum gauge that they just let run all day long for 24 hours. And this was at a piston pump, a reciprocating vacuum system. And it shows you that the vacuum was all over the place here. This is, if you can make that out on the camera, your mercury measurement goes this way, and then this is time, like a clock. So you can see when the vacuum is off, there's nothing. When it's on, though, depending on the number of sweepers, it's all over the place. And they're comparing that to a Spencer system. This one was at the Hotel Turbine in Boston. Observe that the vacuum maintained is almost perfectly constant between 5 and 6 inches of mercury, irrespective of the number of sweepers. This superior result is obtained without the use of any auxiliary governing device whatsoever, because it's a multi-stage centrifugal turbine and it's attempting to keep the vacuum constant, varying the airflow to do so, whereas a positive displacement system is attempting to keep the airflow constant and the vacuum will go all over the place to do so. Well, why would you try and keep the airflow constant when you have variable airflow requirements, is Spencer's point. Actual tests taken from Spencer cleaners. So they've measured the vacuum. They've shown you with a small system, a large system, varying numbers of sweepers. And you can see as the number of sweepers they're trying to get on this one system goes up, the hose diameter decreases, because then each hose requires less airflow. But then, of course, each hose delivers less airflow. So you can get up to 12 sweepers on a 10-horse system if you use 1 1/8 hose, little Arco wand hose. But really, that would be a 10-horse would be more like a 4-sweeper system in practice. Oh, this is neat too. Boy, this is almost a 20-minute video. Ugh. Vacuum cleaner installed at 9th District School, South Manchester, Connecticut. 5-horse vertical. Okay, so first they vacuumed the rooms with the Spencer, and they got 3 pounds of dirt out of the rooms. Then they used a broom, got 14 ounces of dirt with the broom. Then they vacuumed and they got the remaining 2 pounds and 2 ounces of dirt. Indicating, first, the brooms removed less than 1/3 of the dirt. Second, the suction cleaner took the first time from rooms 25 and 27 the same amount of dirt as taken with brooms and suction cleaner, showing absolutely no advantage in using a broom at all in connection with the suction cleaner, and the almost absolute uselessness of a broom without a suction cleaner. This is a study that we should reproduce today, because every commercial space that's hard floor, they don't vacuum. And they should. Steam aspirator, those steam-driven units. Some who have installed them have been obliged to discontinue their use on account of their extravagance in the use of steam. When they run their own steam plant, it only costs about 10 cents per hour per sweeper to operate steam jet equipment. Figuring on the same basis of running their own steam plant and making their own electricity, it would only cost about 4 cents per hour per sweeper to operate our turbine cleaner, besides operating larger tools and exhausting a greater volume of air. This goes into more general kind of data, weights and specific gravity. This is, I guess, like just a little handy chart. I don't know why you'd use this in connection with installing a vacuum, but it's neat. This is like the data that you get in one of those little pocket ref books, or the Farmer's Almanac or something. It's pretty neat, but come on, let's get back to vacuums. Fuse table. Okay, so this is relevant. For a given horsepower motor and a given voltage and a given phase, these are the size fuses you need. Amperes per terminal, alternating and direct current. So take my 7.5 horse machine. AC 220 volts, that gives you approximately 22 amps per terminal at 3-phase. So there you go. Put that in your pipe and smoke it. Conduit table, so if you need to run a given amount of wiring, this is the size conduit you'll need. Equation of pipes. What number of pipes of a given size are equal in carrying capacity to one pipe of a larger size? Same velocity of flow, the volume delivered by two pipes of different sizes is proportional to the squares of their diameters, thus one 4-inch pipe will deliver the same volume as 4 2-inch pipes. But I kind of get lost with the math, but I understand it if they put it in vacuum terms. Okay. This is size of pipe. Oh yeah, okay, so this is pipe size for length of pipe, number of sweepers, and hose diameter. So depending on the length, and you can see they did some big old buildings. You can see in this example, they're talking about a maximum pipe run of 450 feet on a 4-sweeper system. Each 90-degree elbow is equal in frictional loss to about 10 feet of pipe of the same size. So it shows you where to transition down to smaller pipe. So here's your vacuum producer. 40 feet of pipe on the exhaust has to be 4-inch. This says 75 feet of 4-inch here, 25 between the last T-fitting and the separator, 75, and then they go down to 3-inch. And then all your risers are 3-inch until the 7th floor, where they only expect one operator above the 7th floor, and they're going to run 2-inch for the remaining 70 feet above the 7th floor. Typical floor plan of 7-story family hotel and apartment house. Here's your vacuum with the exhaust into the smokestack, and you've got 3-inch going this way with 2-inch branches, and then you have 4-inch going this way until the first branch to the inlet riser, and then you got 3-inch this way, and you got a riser here, 2.5 to the remaining last riser. Piping instructions. Oh, this is neat. Proper way to connect the inlet piping. Steam, gas, or water fittings must positively not be used as they will clog. They give you the felt pad, and I've got a couple of these round felt pads. They're not in terribly good shape, but they're original, so we can't get rid of them. that the machine would sit on, and then they give you these flexible rubber hose sections the size of the pipe to connect the machine to isolate what little vibration the machine actually produced from the piping. Long radius bends should be used wherever possible, especially in case where the horizontal mains are below machine. This is like your workmanship guidelines. Ream to the full inside diameter, all fins removed, screwed home full against the shoulder of the fitting so as to leave a smooth uniform bore. Mains and risers run substantially as indicated on the plans. Size shall in every case be clearly designated and approved by this company or its authorized agent. So Spencer would lay out the system for your building and they'd give you the plan and say, okay, now have fun. Set the machine on the pad without fastening to the floor. Rubber sleeves furnished with the machine must be placed next to turbine in both intake and exhaust pipes and must be straight, not curved. Exposed pipes shall be provided with a nickel-plated floor or ceiling plate. Exhaust shall be connected to a chimney or flue without other opening above basement. Oh, this is neat on the next page. The right way and the wrong way. They're showing you how to make sure your T's are going the right direction, how to avoid dropouts. And this is not a dropout because this is just a clean-out plug on the right here. Horizontally disposed clean-out plugs, otherwise the dirt just goes down and sits inside here. There is actually an application where you do this, where there's heavily abrasive materials being conveyed. Then, the shards of glass or whatever you're sucking up hit the plug instead of wearing through the elbow. At least that's the idea. And this is a dropout, and this would be the proper way to do it. Basement inlet. And yet, 100 years later, I make my living fixing this stuff. So I should just Xerox this and, send it to every low voltage contractor in the Chicagoland area. Horsepower transmitted by belts. See, none of the Spencers were belt driven. This is just like fun data. I feel like this was a promotional thing that Spencer would give away to engineers or architects saying, hey, there's all kinds of useful stuff in here, and oh, by the way, a lot of it's about our product. Okay, now we're at almost 30 minutes, so I'm just going to gloss over square and round bars. Weight of sheets of wrought iron, steel, copper, and brass. Metric system. Avoirdupois weight. Yeah, I slept through science class. I don't know what that means. Yeah, this stuff's kind of interesting. It's useful. I mean, maybe they were trying to get you to keep this as a ready reference to remind the good architect to put vacuums into their plans for buildings. I bet this was a promotional item. Circumferences. Yeah, I don't think any of this last stuff pertains to vacuum. We'll just make sure before we wrap up this extraordinarily long video. Is anybody still watching? Well, thank you. You're a good sport if you are. So that's it. That's the last page. And there's my little Spencer booklet. Hope you enjoyed it. Thanks for watching.